In the initial briefing to challenge the thinking on energy and climate change, understanding the global drivers, we took a close look at climate change, its causes, the greenhouse gases, their sources, and how your organisation contributes to them. We then went on to take a look at energy, how it's used within the UK, and where the inefficiencies lie, and obviously the potential for further improvement. But one of the key points that came out of it was we needed to remind ourselves that we live on a planet which is totally dependent for its functioning on ecosystems. We then extract energy, which is used to extract resources to support the economic system, and as a result of all those economic activities, we have a wide range of negative environmental impacts, one of which is climate change. And the challenge to the thinking was this, that by going for energy reduction rather than energy efficiency or switch to renewables, we achieve a reduction in most of the global environmental impacts. We achieve increased energy security, and at the organisational level, we also achieve competitive advantage. And of course, we also reduce our greenhouse gases. Then we noted that within the UK, 80% of the energy is used for building and transport, roughly 50% buildings, 30% transport. And the good news was that we will be looking to achieve a 50% reduction in that energy consumption, 50% saving tomorrow. Hello, I'm Dave Stanley. In this brief in the series to challenge the thinking, we'll take a closer look at transport, all the modes, and how we can save 50% of the energy tomorrow. Some of you may remember that old British rail ad campaign, "Let the train take the strain." Well, it's as true today as it was 30 odd years ago, but there are some reservations. We'll take a look at the efficiency of each of the modes and where there are smarter fleet and system management opportunities. Well, let's start with a gallon of fuel and see exactly what MPG we are getting and where. With our gallon of diesel, let's just take a look at passenger transport and see what the comparative vehicle efficiency is between the differing modes. And in this, we'll be looking at it in terms of passenger miles per gallon, and we'll be assuming that all vehicles are full. You can see, just walking, if you remember from the earlier briefs, you get around about 500 miles to the gallon. On the other hand, jump on a bike, you're at around 1,000 miles to the gallon. Of course, if you go to a rickshaw, you can double or treble it. High-speed train is up around about 940 miles per gallon, and the underground doesn't do too badly, 640. Trolley bus comes in at about 400. Coaches, diesel, similar sort of figure. The electric car looks quite good at 350 miles per gallon. High-speed diesel train, 310 miles to the gallon, and then you're down to average car, 4 passengers on board, turns in about 130 passenger miles per gallon, and then dear old 747 aircraft, around about 65, hydrogen car 40, and an ocean liner only about 25 passenger miles per gallon. But bearing in mind, you're not just carrying the passengers, you're also taking along ballrooms, restaurants, swimming pools and the like with that. However, these figures are from tank to wheel. If we now take account of the UK energy mix that goes into the electricity system, you'll see that the high-speed electric train drops back to 310 miles to the gallon, trolley bus or tram goes back to 130 miles per gallon, and the electric car drops to about 120 miles per gallon, slightly less than your typical car. Let's just remind ourselves of a bit of the basic physics that's associated with transport. That gallon of diesel has potential energy in the form of the chemicals that are within it, hydrocarbons, into a combustion engine, where that combustion engine releases heat, waste heat, and also moves the vehicle forward. And in moving it forward, it then gains kinetic energy. Now, the basic formula for kinetic energy is half mv squared. In other words, half the mass or the weight of the vehicle times the square of the velocity or speed. Now, what's interesting is that if you turn around and double the mass of the vehicle, then clearly you double the kinetic energy. However, if you turn around and double the speed from say 30 to 60 miles an hour, just take a look at what happens when you're dealing with squares. 30 miles an hour squared gives you 900, 60 squared gives you 3,600. In other words, if you double the speed of the vehicle, you actually quadruple the kinetic energy. What this boils down to is fundamentally that a speed reduction is going to be the largest factor in improving energy efficiency. In addition to the kinetic energy, there are other forces acting on the vehicle, those associated with accelerating the vehicle to speed and braking it back down to a stop. And clearly here, the weight or mass of the vehicle is an important factor, particularly if you're operating in a city where it's constantly stop-start, then keeping the weight of the vehicle down to a minimum is obviously a significant benefit. Another is the aerodynamic drag on the vehicle, or form drag, which is associated with the body moving through a fluid, air or water, and the faster it goes, the greater the drag. Then of course there's the rolling resistance, which is associated for instance with the flexing of the tyres, why they heat up. It's associated with the drag of the oils in the gearbox and in the differential, and that again is affected by the viscosity of the oils. As we go through this brief, I will be comparing the different transport modes with the level of efficiency that's being achieved today with that was being achieved say 50 or more years ago. And the purpose of that is not to turn around and advocate that we go back to the old transport systems, but merely to highlight the lack of focus that there has been on going for energy efficiency in terms of our transport systems. As our North Sea oil reserves decline, we're becoming increasingly dependent upon imported oil and gas to keep our economy going. In this slide here you can see where the oil goes. The largest band at the bottom is road transport. There's two thin lines there referring to rail and water, and the blue one is for aviation. But what it boils down to is that 75% of all oil consumed in the UK goes on transport, the largest proportion of which is road. Let's take a look then what's been happening to that oil consumption in road transport. These are the figures from 1990 to 2007, and you can see that for petrol vehicles it's remained largely static, around about 70 megatons. However, there's been an increasing popularity of diesel vehicles, and there our diesel consumption has doubled from 10 megatons to 21 megatons. That gives us a total for 2007 then of 90 megatons of oil. If you want that in our gallons, it amounts to 18 billion gallons of diesel petrol. This is for road only. That works out at 275 gallons of petrol or diesel per head per year for every member of the UK population. In other words, each day we're burning through 3/4 of a gallon of diesel per day just on road transport. Part of the reason, of course, is the fact that the efficiency of our cars has not increased over the 10-year period from 1997 to 2007. MPG per vehicle has remained at 32 miles per gallon. And one of the reasons why we've not seen an improvement in our overall MPG for vehicles, despite the technological advances one would have thought had taken place is actually straightforward weight increase. And on this slide here you can see that, for instance, over a 50-year period the old Mini has doubled its weight from 600 kilograms to 1140. The Beetle down at the bottom, 860 to 1600 kilograms. And overall, cars on the road today are 50 to 100% heavier than they were 50 years ago. Think of your half mv squared again. So how might we deliver this 50% reduction in energy consumption tomorrow? Well, at the national policy level, there's the issue of pollution prevention. Looking for opportunities to remove catalytic converters and filters from vehicles, which at the end of the day significantly reduce the overall engine efficiency by 3 to 7%. And this could be done by redesigning engines and also changing the fuel type to, say, dimethyl ether. The other biggie, though, back to your half mv squared, is actually reducing the speed limits. It's generally reckoned that for every 10 mile an hour reduction in speed, you get a 10% saving overall. However, I would suggest actually the figure could be closer to 15 to 25%. That would amount to a total reduction in the UK's total CO2 emissions of the order of about 6%. You might think that 15 to 25% is overstating the case. Don't forget half mv squared. But this is interesting. When the price of oil reached $125 a barrel, the Spanish decided that they would introduce a 10-kilometre reduction, 7 miles an hour reduction in their motorway speeds. That resulted in an immediate 8.5% reduction in their total fuel consumption. Now, if you think on UK motorways, most of the traffic, or cars anywhere, are doing around about 80-85 miles an hour. Just enforcing the current legal limit in the UK could achieve something in the region of a 15% reduction. Take that back to 60 miles an hour and you're at around 20-22% reduction. That would amount, if the Spanish saved 450 million euros, about £1 billion a year to the UK. Now let's take a look at another issue where we can achieve similar orders of saving. I'm referring to driver training. In terms of energy reduction within your existing fleet of these things, trucks and vans, an attractive option is going for driver training. Now, whether your fleet is actually owned by you, or you lease it and pay for the fuel, or you lease it and pay for the mileage, it's worth a look. The data in terms of energy, well, you should achieve between 2 and 25% per driver depending on their existing skills, an average of about 15%. In terms of mileage, well, if they're clocking about 15,000 a year, at £1.40 a litre, that's about £300, and there are other benefits. For instance, the data for the UK is that 12% of licence holders are company drivers, yet they're involved in 65% of all accidents and 35% of all fatalities. So what's involved? Well, as ever with environmental management, it requires good management, the 3 M's: measure, monitor and manage. And a good start is ensuring that you're on fuel cards. So you can track the MPG and performance of individual drivers. You can get feedback in terms of the average for that particular vehicle within your fleet, and of course against the national fleet as well. You also get other data. For instance, when I was with the predecessor organisation of the Environment Agency putting in a scheme, an efficient driving scheme, quick scan through the data indicated that one particular depot's fuel consumption was about 30% worse than all the others. Now you go for the obvious things in terms of, have they got a lot of trailers? Were there a lot of hills around? And the answer was no. So a call to them indicating I'd be giving them a visit in a month's time, and what a surprise. A month later, their fuel figures were more or less in line with everybody else's. Another requirement, though not essential, is on the maintenance side. for instance, wear and tear on the vehicles, brakes and tyres. Again, you'd be surprised at the difference in terms of tyre wear, with some drivers getting 14,000 and some getting through to 48,000 out of a brand new set of tyres on the same vehicle, allegedly doing the same job. And you can also guess who's having the most accidents. When it comes to accidents, typically found that they involved either ramming the vehicle in front or alternatively couldn't reverse because they didn't know how to use the wing mirrors. By way of accidents, of course, there's a payback there in terms of insurance, particularly if you're in the government sector, where you will be carrying your own insurance risk. And a reduction in accidents, of course, gives you an immediate payback. If you're doing it through an insurance company, obviously you look to negotiate on the basis that you're doing the training and looking for a subsequent reduction. So what does the training itself actually involve? Well, we're not talking about a 20-minute spin around the block just to show them how to do it. We're talking about actually shifting their mindset on this one and hopefully changing the culture of the organisation. What we're talking about is 3 guys in a car for a whole day, and you're going to put them through the lot. Town driving, country driving, motorway driving, parking, briefings on vehicle safety, checking the tyres, and all the rest of it. And by that, the training is going to be involving all drivers, and that includes you. What's the downside? Well, don't underestimate the challenge of this, because you can criticise a guy's wife, but not his driving. And when you look, guess who is most likely to be the worst drivers in terms of MPG and indeed accidents? They're going to be the ones that are supposed to be setting an example. But what are the benefits? Well, unusually, this is one example where you get sustainability benefits, i.e. benefits in all 3 areas. You get the environmental benefit of energy reduction around about 15% and the associated greenhouse gases. You get an economic benefit in terms of the reduced fuel consumption, tyre wear and insurance. And of course there's a social benefit because the training actually carries over to the driver's family, improves the safety there and also improves their MPG with their own vehicle or when they're driving socially. So the potential of driver training is actually very significant. There's the opportunity there to achieve a cultural shift, i.e. not how quickly can you do the job, but how efficiently and effectively can you do it. Here's a summary of the points that we've just discussed. Pause if you want to take a closer look at them. But let's just hang a few figures on that in terms of fuel cost savings alone. Let's assume you're doing about 15,000 miles a year, 40 miles to the gallon. Fuel is around about £1.40 per litre. You achieve a 15% reduction. That adds up to £350 saving per annum. That gives you about a 6 to 12 month payback, worst case, on the cost of that driver training, plus all the other benefits that we've already discussed. So from the fleet management perspective, how are we doing? Well, there was the fuel cards, and how much you'll save out of that is an unknown. It depends on how effectively your current fleet is being managed. Driver training will take 15% on that. Then of course, you're back to fitting speed limiters. I'm talking about fitting speed limiters to your own vehicles. It's a rather interesting situation where companies are quite content to turn around and supply vehicles to their drivers that are capable of speeds well in excess of the legal limit. Fitting a speed limiter that cuts it back to 70, probably worth about 10%, and it ensures your drivers are driving legally. And of course, well, if we go to 70, why not back to the single carriageway limit of 60 miles an hour, and that would probably give you around about 25% savings. But we won't overstate it, we'll take 15% on that. Then there's route planning. The use of sat-navs is generally reckoned to deliver savings of between 6 and 16%. Not only for ensuring that they go the most cost effective or the shortest route, but also in terms of congestion avoidance. Well, we won't overstate that one. We'll take 5% of that, bearing in mind frequently you're on routes there that your drivers are going to be familiar with anyway. Reduction in vehicle weight. Well, that's worth round about 4% for every 100 kilograms you unload off the vehicle. I'm talking in terms of carrying unnecessary tools, unnecessary seats in the vehicle, even the spare wheels worth a thought if you just think in terms of who is actually capable nowadays of actually achieving a tyre change, or do you call in a company to do the job for you? Increasing tyre pressures. What I'm referring to here is that most people seem to drive around on tyre pressures that are at the 1 to 2 passenger level. If you increase your tyre pressures to the 3 to 5 passengers, then that obviously increases the stiffness of the tyres, reduces the rolling resistance, and that's worth round about 3%. If you want to go higher than that, there are some issues associated with increased tyre wear in the centre of the tyre, and if you're driving at excessive speeds, there's a car handling issue as well. Then there's maintenance, ensuring of course that your vehicles are properly maintained, not only to reduce the emissions but also maximise the vehicle efficiency. Ensuring that you're specifying for low viscosity oils can also help. But another interesting one, of course, is air conditioning. Now, air conditioning is costing you between 4 and 10% of the fuel consumption of your vehicle. For the lighter vehicles, it's 4% just to carry the extra weight of the air conditioning around, switch it on, and the fuel efficiency drops by anything up to 10%. Obvious question is, 10 years ago we used to manage without air conditioning. Why is it there today? So an option is either you remove the air conditioning system, subject to the airflow through the vehicle being maintained, or indeed just pull the fuse out of it. With fleet management, a very important issue is actually vehicle replacement and getting the specification correct. In terms of cars, obviously it's very smart to turn around and go down the diesel route, because a diesel engine is inherently more efficient than a petrol one. Another issue is ensuring that you knock out the unnecessary bells and whistles which car manufacturers are only too pleased to supply you with, but at a cost. Another one, of course, is specify against air conditioning, becoming increasingly difficult, but as we've seen, air conditioning has a significant cost in the overall performance of the vehicle. Also, automatics. Automatics are rarely more efficient than a manual gearbox where the driver knows what they're doing. And indeed, automatics are always more expensive to procure in the first place, and also more expensive to maintain. Then again, there's the issue of acceleration. Well, do you actually need 0 to 60 in 10 seconds or whatever? A more realistic acceleration rate means you can get away with a smaller engine, and it should mean higher efficiency. So it's important you specify for the whole life costs of that vehicle in terms of not only the fuel consumption but also the maintenance, and specify for the performance that you and your organisation actually need rather than what the drivers might like. Vehicle operation. Well, it goes without saying that good route planning can make a significant difference to your overall fuel consumption and also wear and tear on the vehicles. In terms of freight vehicles, always maximise the load capacity and also go for backloading, i.e. make sure you're not coming back empty if you can avoid it. And on the car side, car sharing in terms of going to meetings or whatever with other employees, and that frequently comes down to ensuring that you're paying a realistic passenger rate which incentivises to people getting together or more to use the same vehicle to go to the meeting or whatever. In terms of vehicle management, it's a statement of the obvious that if you turn around and target mileage reduction, in other words looking to see where journeys can be eliminated, either using video conferencing or whatever, or if the journey is actually necessary, taking the train or public transport, you're not only going to save on the fuel, you're also going to reduce the wear and tear on the vehicles themselves. But if you add to that, when you turn around and re-specify for the next vehicles coming into your fleet, ensure wherever practicable that you actually go for doubling the MPG of the existing vehicles. Then that should result in a 75% reduction in the overall energy consumption of your car fleet, and of course a reduction in the wear and tear and other costs associated with maintenance as well. If you're looking to specify your next vehicle in terms of fuel efficiency, you might be tempted to turn around and use the government data in terms of CO2 emitted per kilometre. Now this is quite interesting. Just take a look at this one. There's two vehicles here. One is the Toyota and the other is the Fiesta. Now the Fiesta's got a 1.6 engine compared with a 1 litre on the Toyota, i.e. it is 60% greater. The amount of power it generates is 40% greater. The weight is about 20% greater on the Fiesta, and the top speed also of the order of about 20% greater. Yet, according to the data here, they're emitting 99 kilograms each. Now something's not quite right there. Now, yes, it is important to be aware of the opportunities to turn around and operate a vehicle with zero road tax, but when it comes to the efficiency of the vehicle in terms of MPG, which is the bit you're going to be paying for, these CO2 emission figures are unmeasurable. Looking for the fuel card data, that's where you'll turn around and find out what's actually going on. Just for comparison, here's a few old vehicles. The 1948 Bond, that did 85 to 100 miles to the gallon. You'd want to travel in one of those, mind you. 59 BMC Mini did 61 miles to the gallon. And the VW Lupo 1.2 went round the world and turned in 116 miles to the gallon. There are vehicles out there that'll do a lot better than 40 or 50 miles to the gallon. With the current focus on reducing greenhouse gases or CO2, there is quite a push to go down the electric car route. And you can see on this slide here that compared to a 1.6 diesel, in terms of the CO2 emitted, the UK going the electric vehicle route gives you about a 25% reduction. And if you look at France, it's of the order of 90% reduction. Now, this does not relate to energy efficiency. The reason for the significant reductions in CO2 is partly down to renewables, but predominantly down to the use of nuclear power. Hence the reason why Greece, which is I'm not even sure it's got any nuclear power stations there, is up above the line in terms of the efficiency of the it's up above the line in terms of its emissions of CO2 compared with a diesel. But what about an energy comparison between these vehicle types? Let's have a closer look at the energy efficiency of electric and diesel cars. Here we've got two broadly similar vehicles. You've got the Renault Fluence electric and the Ford Focus diesel. Power is more or less the same. Weight, well, the electric inevitably is heavier because it's got the batteries on board. Top speed, well, the Ford Focus goes some 30 mile an hour faster. But in terms of the fuel efficiency, the Ford Focus is 25% more efficient than the electric vehicle. Now, there's a number of reasons for this, not least of which, of course, is the fact that if you're comparing two vehicles, like for like in terms of range, then a diesel with a 50 litre tank compared with an electric vehicle, the electric vehicle will require batteries weighing 2.5 tonnes, half mv squared bit again. So there's an interesting fiscal issue here. There's a push to go down the carbon reduction route and giving tax incentives on that side, but maybe also we ought to be looking at taxing or influencing people to go down the energy reduction side at the same time. In terms of road infrastructure, well, in terms of the whole life costs of roads, 40% of it is down to the operational side, and there's opportunities for savings on lighting, for instance, of the order of 40 to 60+%. To conclude on road transport then, there's the obvious issue of reducing the need to travel in the first place. And WWF, in a report called Moving On, had surveyed 150 odd companies, and they came to some fairly obvious conclusions that the benefits are to be found in a reduction in travel budgets, reducing the carbon footprint, i.e. your energy consumption, but also increased flexibility of staff and their improved work-life balance. Reduction in disruption as a result of breakdown in the train system, or cancellation of flights due to weather or whatever. But the most important one down here, look, is the new culture of working and collaborating, questioning the need to travel in the first place, and then also seeking to do it in the most efficient way that they can. Let the train take the strain. Let the train take the strain. Well, from the energy perspective, the logic's undeniable. If you're driving yourself to a meeting, then average MPG 30 miles to the gallon. Take a train, even if it's only half full, you're turning in about 150 passenger miles per gallon, which represents an 80% saving in energy. But what about the economics? I think everybody recognises that first class travel is exorbitant, particularly if you're going in and out of London. And if you drive yourself, then you're just looking at the marginal cost, 20 pence per mile. But what about the whole journey costs? Now let's say you're earning £50 an hour, you're earning more, factor accordingly. Then in terms of your time on the train, if you assume that 80% of that time is actually working, preparing for the meeting, reading papers and so on and so forth, then what it means is that for every hour that you're on the train, you can deduct £40 from the price of the ticket. If you want to look at it from the other side, looking at it from the car, if you're driving yourself, average 40 miles an hour, that means it's costing you £1.20 per mile for your wasted time whilst you're doing the driving and not carrying out any other work. Furthermore, you can add to that the fatigue and stress of doing the driving as opposed to being on a train. You may recall from that first bar chart that a full high-speed train, diesel or electric, wheel-to-wheel, turns in round about 300 passenger miles per gallon. Part of the reason for this, of course, is the low rolling resistance as it's running on rails, and another is the aerodynamic drag on it, low frontal area, probably about half that of a double-decker bus, and of course it's long and thin. As for the weight of a high-speed train, it's quite staggering. It's almost a ton per passenger. Not there's much you can do about that. And similarly, there's not a lot of point in slowing down a high-speed train. So where are the opportunities to be had in the existing system? A couple of years back I was supporting an engineering company in developing their sustainability strategy, and the director was particularly committed to it. So the first thing we did was take a look around their workshops, which was pretty substantial. Went to the workshops and took a look up, and the skylights were not unusually dirty, but all the lights were on. So I said, okay, well let's turn all the lights off in this building and just see what effect it has on the ability to carry out the task. Well, there's a bit of huffing and puffing, and about half an hour later one of the managers returns to say that they finally found the light switch, and it's in the premises next door. To which the obvious question was, well, where's the meter and who's been paying for it? And the answer was, this office next door had for 3 whole years been paying for the electricity for this particular workshop. So what's the connection between that little story and the railways? Well, the connection is this: the lights are on. And the situation with the railways is they're largely unmetered. And indeed, the continental railway system's in the same state. There is one exception. London Midland have in the last year or so metered all of their trains. No measuring, no monitoring, no. It comes to metering trains. This is an interesting one. About 5 years ago, the Swedes actually installed a meter on a single traction unit and ran it for a complete month. And what they found was that over that period, same train, same route, there was up to a 50% difference in the energy consumption. Now that would be down to a whole range of issues associated with traffic management there, driving technique, load and so on and so forth. But it gives an indication of the potential for further improvements in the efficiency of train management once you turn around and measure, monitor and of course manage. In terms of the railways delivering a 50% reduction by tomorrow, what are the targets or incentives? Well, take a look at this. This is from the Intercity West Coast franchise that was issued in May 2011. And from the Sustainability and Environmental section, it says, bidders may wish to consider improving the energy performance of stations and consider modifying trains to provide more accurate information on electricity consumption, for example, through fitting electricity meters. The Climate Change Act of 2008 actually requires the UK to deliver a 34% reduction in energy consumption or CO2 emissions by 2020. It doesn't look as if the railways are being expected to make a large contribution to that reduction. So with trains, how does the new compare with the old? Getting hold of the data on that was rather tricky, but what we have here is a replica of a steam locomotive that was built by a group of steam enthusiasts. The project was finished a couple of years ago. It's called the Tornado, and it would appear that this thing turns in about 50 grams per passenger kilometre. If you think in terms of road tax, less than 99 grams per kilometre is reckoned to be good. What about the actual efficiency? Well, probably the old steam locomotives were around about 8% efficient. Diesels today around about 20%, and it's reckoned that applying the latest steam technology to locomotives, they could be of the order of 40 to 50% efficient. We've been largely looking at the operating costs, the fuel costs associated with the various transport systems. But that's only part of the story. There's the whole life costs associated with any one transport system. Not only is there the operation of the vehicle itself, there's its maintenance, its manufacture, its disposal, there's the garages, the infrastructure to support the track or road system, there's insurance and so on and so forth that go with it. Let's just take a quick look though at the differences between the various transport modes. I couldn't find a European or British report looking at total infrastructure costs, though there is one actually being put together at the moment. This is actually an American one, but they will not be too dissimilar. In terms of cars then, the use phase is shown here, and the infrastructure costs are an extra 50% on the use phase in terms of energy consumption per passenger mile. For a bus, you can see that the infrastructure here is somewhat reduced at 35% because of the higher utilisation. For aircraft, the infrastructure costs are only 20%, and obviously the reason for this is you've only got the airport. Yes, there is some infrastructure associated with the air traffic control system, taking it from one airport to another, but that's fairly minimal compared with road and rail. And it also explains why large countries, China being a good example, if they're looking to rapidly expand their transport system, going the aviation route is the cheapest option. In fact, you may have heard that China is looking to build another 100 airports by 2020 in order to improve its transport infrastructure. By comparison, rail, the infrastructure is quite high in terms of the track, the trains, maintenance there, the railway stations. It's an added 130%. And what that implies is that in terms of the railway, if you're looking to increase your efficiency, maximising the use of the existing system is the most expedient way forward. By comparison, as high-speed trains are being looked at as a means of increasing the transport capacity in the UK, the old half mv squared bit kicks in. And you can see from this here that a train operating around about 100 miles an hour and one operating at 200 miles an hour, basically it doubles the energy consumption. And also there are some very, very high infrastructure costs associated with putting in a high-speed train system. Maritime boats. How are we going to achieve a 50% reduction in energy with these? Well, there's a number of opportunities through fairly simple, straightforward upgrades. These include hull coatings. In other words, improving the slipperiness of the hull, and with modern coatings that's reckoned to be worth up to say around about 5%, and hopefully we'll be using something a little smarter than TBT, tributyl tin. Another opportunity lies with energy recovery systems behind the propeller, post-swirl devices and thrust systems on the rudder itself. Then the propellers can also be improved by increasing the size, reckoned to be worth about 4 to 10%, and also by fitting tips to the propellers, there's up to about another 4% to be had there. Surprisingly, engine upgrades, which you can imagine is going to be a potentially fairly expensive capital item, is reckoned to be only worth up to about 1%. Then a ship's obviously going to have pumping, lighting, fan systems on board, and there's going to be opportunities there, small in comparison to the overall energy costs associated with the vessel itself, but potentially worth having. That lot tots up to around about 20% in total if all of those upgrades were to happen. There's more to come yet. You've guessed it though. This is from the International Maritime Organisation's report on reducing greenhouse gases from vessels, and it looks at the relationship between speed, engine power and fuel consumption. And as you can see from this table, a 20% reduction in speed gives you a 50% reduction in energy consumption. What that comes down to is a 5-knot reduction from 22, 23 knots down to 17, 18 gives you that 50% reduction in fuel. There's still more to be had though. Here's an interesting one. The fitting of sails to vessels. This cargo vessel here happens to be carrying wind turbine components, and as you can see there's a kite system attached to the front. The fitting of these sail systems is actually fairly straightforward, and it's reckoned to deliver an energy reduction of 10 to 15% by capitalising on the wind, subject to the direction of the wind relative to the vessel of course. And talking of wind, what about historical performance? Well, this thing here is a wind jammer. They were around from about 1870 to 1900 or so, made of steel. They carried up to about 8,000 tons. Average speed 10 to 16 knots, and the crew on them was between about 15 and 30. Fossil fuel input, yes, there would have been some, heating, lighting, cooking and so on, but it would have been very small in comparison to modern systems.
You can go VS now, I suggest. About 200 feet a minute, you're perfect. Because otherwise it'll just level off 3,000. But you don't want to.
Aviation, planes. A Boeing 747 will turn in around about 64 passenger miles per gallon if it's full. And you need to remember that in terms of the global warming potential on account of the water vapour, you need to multiply the CO2 emissions by 3. But an even bigger factor with aviation is the sheer speed at which it's expanding. Here's a forecast by the Department for Transport done in 2011 that reckons that by 2030 there will be a 40% increase in passengers flying from the UK, and by 2050 it will actually double. Now, you need to remember that the aircraft that are coming into service today will be around in 20 or 30 years' time. And the opportunities for improving the efficiency of the existing fleet is somewhat limited. And let me explain to you why. This is the speed against drag curve for aircraft. Increasing airspeed along the bottom, increasing drag up the side there, and the energy to counter it. The curve here is the one that we've seen associated with cars and trains. Increasing speed, significant increase in the form drag. However, with aircraft, there's another form of drag called the induced drag, and that's the drag that's associated with getting the aircraft to fly to generate the lift. And fundamentally, at the lower speeds, there's a high angle of attack, high drag, and as the speed increases, the angle of attack decreases, and along with it the drag, as you see here. So the total drag associated with an aircraft is shown here, and this point is what is known as the minimum drag speed, the point at which the least energy or least fuel is required to maintain flight. What is interesting though is if you get yourself on the wrong side of the drag curve, you find that as the speed decreases, you require yet more energy to stay there. And this is known as being behind the curve, behind the drag curve, which you've often associated with work. Stuck on your desk there, you put in a bit of extra energy to try and clear it. You find you've still got more to do until you reach the point where you have a nervous breakdown, stall, crash, exit the organisation and find yourself seeking employment elsewhere. Now, in order to get yourself from the wrong side of the drag curve over to here, you actually need a serious fistful of throttle to do it. So you get to a point here which is the optimal point, whereby if there's a small variation in speed, you don't find yourself on the wrong side of the curve, and the engine fit for a particular aircraft will be optimized so the engine are most efficient at that point. What this comes down to is then that for any one aircraft type with one engine fit at one weight, there's only going to be one speed and one altitude that will give you fuel efficiency. Slowing down is just not an option. So when you're flying on a long-range aircraft, you'll typically find the aircraft, for a modern turbofan anyway, will probably initially level off at, say, round about flight level 300, 30,000 feet, and as the aircraft lightens due to the fuel being burnt, the aircraft will progressively step up to 40, maybe 42,000 feet, the point at which it's then generating the maximum fuel efficiency. So the opportunities for improving the efficiency of the aircraft are somewhat limited. The weight of the aircraft is fixed, the fuel is a variable according to the range that it's going, and the bit in the middle, the load, is where the maximum efficiency can be achieved by absolutely maximising the load capacity of the aircraft. In other words, pack as many passengers as you can in. That's how O'Leary partly makes his money, and then you make up the difference in the cargo hold by taking freight. Let's see what's been happening to aircraft efficiency over the years. Here we've got energy per available seat kilometre, and it's been indexed for the Comet coming into service around about 1960, and you can see that there's been a progressive improvement in aircraft efficiency through to about 2008-2009, with the latest A380 coming into service. However, what's particularly interesting are these blobs over here in the 1950s, and that, would you believe, is for piston-engined aircraft. And the situation today is that your modern jet aircraft is actually no more efficient than a piston-engined aircraft was in the 1950s. Yes, but they're more reliable today, they crash less often, and so on and so forth. However, I'm sure by now you understand the reason for that. With the existing fleet, there are some opportunities for some improvements in efficiency. The retrofitting of the small fins on the wingtips that reduce wingtip vortices are reckoned to achieve an efficiency of between 3 and 6%. The upgrading of the auxiliary power unit, that's the small turbine that operates on the ground when the main engines aren't operating to keep the services going, they reckon there's efficiencies of 1 to 3% to be had there. Also, there's engine retrofitting, and surprisingly they only reckon there's 1 or 2% to be had out of that. And in addition, there's other improvements that can be had in terms of improving the lighting, some of the fans and so on within the aircraft. But the total that there is somewhere between 7 and 13% to be had by such retrofits. A couple of years back, the Department for Transport came out with a report entitled UK Aviation Carbon Reduction Futures, where they came out with the statement that the strongest commercial driver for reducing CO2 is the role of fuel prices in stimulating improved fuel efficiency. In other words, if you put the price up, it didn't half get their attention. Well, what might they be referring to there? Well, back in 2008, with the significant hike in fuel prices, within the EU, they've, within a 6-month period, found 5% efficiencies within European airspace. But there's significantly more to be had out of aviation within the existing fleet through traffic management. Take the simple situation where aircraft are queuing for takeoff, all 2-4 engines running there, wasting fuel. The takeoff itself is not always necessary, for instance, to go to full power. Sufficient runway and also a lot of power available on modern jets, you can save some there. Further improvements are to be had in routing, but some of the most significant ones are actually to be had in the approach and landing. I think most of you will have heard of the stacking, for instance, that takes place over Heathrow and other major airports, where the aircraft are progressively cleared to a lower and lower height, held at each height, consuming far more fuel than they would have been had they been at the greater height, and obviously reduced efficiency with it. There's a system called continuous descent and approach, whereby with the right planning the landing slots arranged and the aircraft maybe 100 or more miles out cuts back on the throttles and just does a continuous approach in to land and saves a very useful amount of fuel. The one flight that I've done in about the last 10 years or so was a bit of an emergency flight from Birmingham to Aberdeen, and the train just wasn't an option. And we took off, flew to Aberdeen, but the approach into Aberdeen, quite frankly, was almost unbelievable. The descent was hanging on the air brakes all the way down, and then there was a long drag around to the north to land on the southerly runway when there was next to no wind. I should think it probably added about 5% to the flight. And by the way, the airports at both ends, I should think with the energy that was going into them, you could have fried an egg on the roof. In terms of a fuel efficient approach, this clip here is from the business end of the jet, and it's my best man Cyril bringing a Boeing 777 into Heathrow. Now, Cyril's done his time on fighters where it wasn't too unusual to find yourself bringing a jet back to base, looking at the fuel gauges and sucking your teeth, which tends to engender a particularly sharp approach to fuel management. And if you listen carefully, it is an open mic. You can hear that the gear goes down pretty late, 2,000 feet flap, and although the co-pilot is actually doing the flying at the time, they are taking a bit of a tailwind. Unfortunately, the aircraft appears to be floating a little too far down the runway. Cyril steps in, takes control, gets it on the ground a bit faster and pulls off, and then they taxi clear. Here we go.
You're down?
Like gears down.
You're down?
Yes, gears down. Flaps going.
Good, let's leave November on the 0 down the right. Clear for takeoff, took this bit.
Gears down. Landing flaps.
30, approaching 40 and 8.
Chile, Victor, take a left turn, hold at November 11 band, with time to 0J. Let's land behind the RJ, November 11.
Land 3. Landing checklist complete.
Landing checklist.
You see Delta, 0 down right, clear land, took this bit to 2 and 2 feet, flight up.
Today with 12 Delta, clear to land 9 right.
Enter 55
2 knots, it says slight tailwind at the moment.
Zero down right by November 11.
Everything is fine.
November 11, speak back to the flight back. Clear 574 right, left hold, November 115, the company AV20. Right, left left hold, November 11 with London 320. Twist 57, don't contact weather controls on standard frequency 129.075, bye-bye. 129.075, bye-bye, 57. Good to leave November, contact weather controls on standard decimal 775, bye-bye. Oh, looking for 1.
Minimums.
Continue.
Slight tailwind.
202, can you straight ahead, hold short Yankee.
50, 40, 30, 20, 10.
Light off? Yeah. Going 777 light off. Okay, here we go.
Ground at 2 train, just vacating 09 left. Good, 2 feet, and then Alpha Charlie, stand 542. Alpha and Charlie, 542, copy. Minute 7 Foxtrot, have to monitor the tower when at decimal 5. They'll call you if they want you from the intersection or not. Okay, monitor 185, number 5, 7 Foxtrot. Give it 59, monitor the tower 185. Bye-bye.
Well, that's fleet management. But what about the business management side and flying? Well, here's another extract from that WWF report, Moving On, where they surveyed 150 odd companies on what they were doing on the flying side, and 47% of them said they've reduced the number of business flights in the last 2 years, obviously due to increasing costs. 63 of those companies do not intend returning to business as usual, and from this group the majority agreed that it was actually possible for a company to fly less and both remain profitable and competitive. Here's a good quote from the head of corporate and social responsibility for the First Group PLC. We've achieved a reduction of 33% in business flights, which has resulted in a 41% reduction in our total travel spend. Well, that's all very well, but what about the personal side? If you're looking to reduce the amount of flying that you're doing, does that mean that overseas holidays go out the window? Well, not quite. Have a look on the internet if you still want to go to the south of Europe for your sunny holidays there, and tap in the Man in Seat 61, run by one-man band there, and what it does is coordinate the timetables from the UK to just about anywhere in Europe, ties in with the night sleepers, even tells you how to get from one platform to another. In delivering a 50% reduction in our energy use, the first consideration must always be to examine the necessity for the journey. Overall reduction in travel delivers more than just energy and cost savings. You may recall from the question and answer session, we spent 50 man days per year, that's 10 working weeks travelling, largely by car. So reducing your travel not only improves your quality of life, but also that of those living along your route. The vast majority of UK's increasingly imported oil is consumed by road and air, and there is a consequential supply security risk to our transport system. Road, but with vehicles, a speed reduction along with a range of other measures can deliver a 50% saving. This to be supplemented by a serious performance efficiency specification for any future vehicle replacements. For rail, whilst you should let the train take the strain with the very high passenger MPG, the reservation is that the railways are largely unmanaged, so there's more to be saved there. On the marine boat side, it's straightforward. It's a half MV squared. 5 knots off the speed gives you 50% off the fuel bill. Air, in contrast, from the basic physics, the options for increasing the efficiency of planes is limited. However, reducing your flying has the additional benefit of significantly reducing your carbon footprint. Remember the global warming potential multiplier for aviation arising from water vapour. The challenge is that we should be seeking to change the culture away from automatically jumping into these or into planes to that of questioning the need for transport, and then if necessary considering mixed mode solutions from walking, public and private transport that offer us the optimal low energy solution. The 3 M's: measure, monitor and manage your energy use in terms of MPG, and with smart targets, delivering a 50% reduction in our use of transport energy should not be difficult. The benefits of financial savings, increased competitiveness for your organisation, climate change mitigation and the quality of life are worth it. Go for it.